This question asks about formic acid, which has a pKa of 3.75. The question asks for the pH when we add 250 milliliters of 1 molar NaOH to 1 mole of formic acid in 100 milliliters of water. The first thing to recognize is that we have a weak acid, formic acid, and that we're adding a strong base, sodium hydroxide. So the reaction between these two species is that if we take our weak acid and we add a strong base, the strong base is going to react completely as much as it can. It's going to consume as much of the weak acid as it can to make the weak conjugate base, which is now going to have sodium as its counterion, and we will make water. So what's happened here is this OH minus from the sodium hydroxide has taken this hydrogen off of our weak acid. If I write out my Rice table, so I have reaction, initial, change, and equilibrium, I'm going to use moles in my ICE table. So I have 1 mole of formic acid, so that's my initial moles here, so 1 mole of formic acid. For sodium hydroxide, I have 1 molar, so that's 1 mole per liter. And I've added 250 milliliters, which is 0.250 liters, so that means I have 0.25 moles of strong base that I've added. So my initial here is 0.25 moles. Our initial conjugate base is 0, and I'm going to ignore water. Now for the change, sodium hydroxide is a strong base, so it will react as much as it can. So I'm going to write minus 0.25 moles because this base is going to react completely and react with 0.25 moles of weak acid. The weak acid is in excess, so our strong base, all of it will react. It will react completely. If we have minus 0.25 over there on the right, we need to have plus 0.25 since the stoichiometry is 1 to 1. And thus at equilibrium we have 1.0 minus 0.25 moles. So that is 0.75 moles. At equilibrium, we have no strong base left, it's all reacted, and at equilibrium, we have 0.25 moles of our weak conjugate base. Now we see that we have a weak acid, formic acid, and a weak conjugate base, the formate anion, and we have them in roughly equal concentrations. We have 0.75 moles and 0.25 moles, so this is within that 10 to 1 ratio window. So this is now a buffer, and we can use the Henderson-Hasselbalch equation. So now we can say the pH is equal to the pKa plus the log of the moles of conjugate base over the moles of conjugate acid. The pKa is 3.75, so this is equal to 3.75 plus the log of our base, which is 0.25 moles, over our acid, which is 0.75 moles. You could also calculate out what the new volume was by adding together this 250 and 100 milliliters, but because the base and the acid have the same volume, if we were to put these two in as concentrations, the volume would simply cancel out and the math would work out to be the same. So in a buffer, it's okay to use moles instead of concentration, but only in a buffer. If we do this calculation, we would find that the pH is equal to 3.27. So when we add this strong base to the weak acid, we end up getting a buffer solution because it makes some of the conjugate base, and we get a pH of 3.27.